All right, so our next unit is over gases, and again, it's going to be kind of covering, we're going to be jumping back and forth between chapters 12 and chapter 13. We're going to start off in chapter 12 today and then get into chapter 13 with some of our gas calculations. So first, we're going to talk about what we call the kinetic molecular theory, which that is in chapter 12. And it just kind of describes how gases do what they do, or how they behave, I guess you could call it, just different characteristics of gases. And different sources list these in different amounts. I can't remember how many steps I have in here. But they're all saying the same thing. They're all describing how gases behave. But as we've already talked about throughout the year, gases are made of these little teeny tiny particles, and they try to be as far apart from each other as possible. So they'll spread out, and we'll talk more about that in a little bit. They spread out very far apart. And these gas particles are in constant motion. So they're constantly moving all around as they are in a container or wherever. And as they're moving around, they're colliding with other gas particles as they're moving around. They're colliding with you, your table, your iPads. In fact, the air that you're breathing in right now, you can't see or feel it, but as you sit here, you have all these gas particles bouncing off of you, and when they hit something, when they collide with you or another gas particle, it's just like how bumper cars, when you run into another bumper car, you bounce back and go the opposite direction. That's what these gas particles do. So as they collide with you or other objects, they bounce off and go in the opposite direction. So that's what we mean by their collisions are elastic. So when they collide, they don't just come to a stop. And for our purposes, when we do the calculations we're going to do in this chapter, we're going to say that they have no attractive forces between the gas particles. Now, as we learned way back when in first semester, we said that, there are London forces between most gas particles, have just London forces, but we're going to assume that there's no attractive forces between gas particles, and that makes our math a lot easier to do. Obviously, if we were working for NASA and needed to, figure out gas stuff with them, we would take that into account because it does make a slight difference, but we're not going to worry about that. And then we'll talk more about this as well as we go through the notes. The average kinetic energy, that's what the KE stands for, the average kinetic energy of a gas, and we talked about this back in the end of first semester. Kinetic energy is the energy of movement. So the more or faster gas particles are able to move, that is related to its temperature. So as the temperature increases, the gas particles have more kinetic energy, so they're moving around more. So I've got it divided up into 5 parts. The book, I don't know, maybe has 4 parts or whatever, but they're all saying the same thing. So no matter where you look up the kinetic molecular theory, it's going to say the same thing. It just may be divided differently. Okay, so our main focus is, and calculations we're going to do today are based on 3 different things about a gas: its volume, its temperature, and pressure. So as we'll see in a little bit, as we change one of those things, that affects the other. And back in our mole chapter, when we first started talking about gases and doing calculations with gases, we said that for our purposes in the mole and stoichiometry chapter that the gases that we're going to do calculations with are always going to be at STP. So again, that's standard temperature and pressure, which again is 0 degrees Celsius and 1 atmosphere. And that's about outside what the pressure is 1 atmosphere. Luckily, we're no longer at 0 degrees Celsius. We're more at around 20, 22-ish degrees Celsius. But now we're going to be, in this chapter, we're going to be looking at what happens to a gas when it's not at STP. How does that affect it being at different temperature and or pressure? Now, this standard pressure is based on the atmospheric pressure. So again, the gas around you that you're breathing in right now is air pressure, the air or atmosphere. And what we consider normal air pressure is the air pressure at sea level. It's based on sea level, which Indiana, we're a little above sea level, maybe about 100 meters or so, but we're pretty close. So, and it varies every day. The pressure goes up or goes down depending on the weather that we're having. And the way we can measure the air pressure is, oh, well, I'm getting ahead of myself, sorry. What the air pressure represents is those collisions of the gas particles. So the more collisions there are of the gas particles, the higher the air pressure, and the fewer collisions of the gas particles, the lower the collisions. And so that's what these pictures here are showing. They're actually showing a barometer, kind of a very old-fashioned barometer that the barometer was first created, I don't know what year, long time ago, way back in Italy, where a guy named Torricelli took a dish of mercury and then put a tube in it that had measurements, just like on our meter stick here. And at standard atmospheric pressure at sea level, the air is pushing down on the mercury and it forces it up into the tube. And so standard atmospheric pressure in terms of the column on the thing is right here. It went all the way up this high to 760 millimeters of mercury. So this is how tall it went all the way up into this tube. So that's another unit. I'll put the units up here in just a minute that correspond to 1 atmosphere. And then you can see over, if we look at the air pressure up on Mount Everest, as we go higher up into the atmosphere, the gravity has a less attractive forces. So the air molecules, there's fewer of them and they're spread out farther. So there's not as many collisions, so the air pressure is a lot less, where up on Mount Everest, it's only going up to about, about right here. So 253 millimeters of mercury. Okay, so that's why people who climb mountains and stuff like that, they need oxygen tanks as they get higher up, above a certain level. They have to have oxygen because there's so little air. And that's, the air pressure is much lower. And even here, obviously Mount Everest is on the other side of the earth, but even if we go to like Colorado in the Rocky Mountains, that elevation, they're so high up in elevation compared to where we are, they have to cook food differently because of the air pressure and how that affects water boiling and stuff like that. And we'll talk more about that later on. So again, we've already talked about 1 atmosphere is considered standard pressure, but there's lots of other pressure units that we'll use in this chapter. The other one that we were just talking about that is showing here on the barometer, that is 760 millimeters of mercury, which literally represents the length of that column of mercury that it went up. The other name for that, for the scientists who came up with the barometer, is also called torr. So you may see that instead of millimeters of mercury. And then the other one that we'll use is 101.3 kPa, which stands for kilopascals. All of these actually are metric units. But kilopascals is 101.3. So all three of these are equal to each other. So we can convert back and forth between each of them by putting them in a ratio. Okay. Now there's lots of other pressure units. Another one, and we won't really use these other ones, there's bars or millibars. If you listen to the news and they talk about the weather, or on your phone app and you look at where the pressure is on your phone app, it probably gives it to you in inches of mercury, which standard pressure in inches of mercury, if we were to flip this around to the inches side, so here we are at 760, and we flip it around and we're right here at 29.9 inches. So that's standard pressure in United States measurements. And then anybody ever pump up a basketball or tire? What pressure did you probably look at? What units were probably on your tire or basketball pump? Nobody ever do that? How about PSIs? Heard of that? No? Okay, well, PSI stand for pounds per square inch. That's another English unit because of the inch here. And that is, I always forget this one, I think it's 14.7. Yes, 14.7. So all of these represent standard pressure. We won't use these three in class. You would see them in your daily lives though, maybe not. But we'll use these three. So say we're trying to figure out what the pressure is of, let's just say 0.66 atmospheres, and we want to figure out what that is in kilopascals. So again, just like with the mole chapter, since all three of these things are equal, we can put them in a ratio and put the 1 atmosphere in the denominator to cancel out atmospheres, and if we want to convert it to kilopascals, we put the 101.3 kilopascals in the numerator, and then we just plug it in, which would be 66.9. Okay, so these are the three you need to know and be able to convert back and forth to those, because we'll be using those pressure units all throughout this chapter. Everybody good somewhere? Okay, now this slide I'm going to go through pretty quickly because we've talked about this several times throughout the year, and also probably in your other science classes. So just, we talked about the kinetic molecular theory. How can we compare gases then to solids and liquids? So again, just the real basic definition of a solid is something that has a definite shape and definite volume, like your iPads, desks, things like that. And they have a definite shape and volume because when we look at it in terms of the kinetic molecular theory, their particles are packed in as close together as possible. And and that's what that first picture on the left up at the top is showing. So their molecules are squeezed in as close as they possibly can, and they're really not moving at all. They have very little kinetic energy. They're just kind of sitting there and vibrating in place. And because of that, because they're packed in so close together, they have a very high density. So solids have a higher density than liquids or gases, except for water. Water is unique. We'll talk about that here in just a second. Then liquids, they have no definite shape, but they have a set volume. So liquid's going to take on the shape of whatever its container is, but it's going to have the same volume regardless. And that's because in liquids, their particles are a little looser. They have a little more space between them, so they can move around more, so they're able to take on different shapes. And because they're spread out more and looser, they have more of a medium density compared to solids. But again, that's not true for water. Water is actually very unique. Liquid water is more dense than solid water, which is nice because that allows your ice cubes to float. If solid water was more dense than liquid water, your ice cubes would be stuck down at the bottom of your glass. Lakes would freeze from the bottom up. That would be really bad. So water is the exception to that rule, and they're able to move around a little more because, and they're more loosely put together because of more of a medium kinetic energy. And then finally, gases, they have no definite shape or volume. They will spread out to take on the shape and the volume of any container. And again, as we were talking about on the last slide with the kinetic molecular theory, that's because gases have such high kinetic energy, so they're moving all about, they're spread out as far apart as they can be from one another, and that gives them a very low density. That also makes them able to be what we call compressible. So the air in this room, even though it's spread out to fill up the entire volume and shape of this room, we could take the air in this room and compress it down into a teeny tiny little container because of how much space there is between the gas molecules. So, and we'll talk about that more, and that's what little cans of compressed gas and things like that are. Aerosols and stuff, they've compressed those gases into a smaller object. And then going from the different states of matter back and forth between solids, liquids, and gases, again, these you should already know. Solid to a liquid is melting. Liquid to a solid is freezing. Hopefully we won't have any more of that this year. Liquid to a gas, evaporation. Gas to a liquid is condensation. And then the two that you may not be as familiar with are these two here, because we see these all the time, these four all the time in our daily lives. But going back and forth between a solid and a gas, those are a little harder to observe. A solid to a gas is called sublimation, and that's actually what dry ice does. Dry ice is frozen carbon dioxide, and it's so cold, carbon dioxide freezes at like about negative 40 degrees Celsius, which is really cold. So then when you stick it in room temperature, it's gaining so much kinetic energy so quickly from the change in temperature that it skips the liquid phase and goes straight to the gas and makes all that smoky stuff that people use carbon dioxide for. And then the other one, going from a gas to a solid, that is referred to as deposition. And that's actually what frost is. Was there any frost this morning? I don't think there was. I know the other day there was frost on windshields, and that's when we have kind of warmer, moist days, so there's a lot of moisture in the air, gaseous water, and then when it gets really cool very quickly at night, that water vapor that's in the air can freeze onto surfaces like your windshield or the grass and things like that. So that's referred to as deposition. So hopefully most of that is a review for you, that you've heard of this stuff before. Okay, so then now we're going to look at more of how the fact that gases can be compressible because there's so much space in between them, how that can affect the other properties of the gas. So because there's so much space, we can compress gases. Like I said, we can take the gas in this room and can compress it into a teeny tiny little container. But there's some things that will affect that. So if we do compress a gas and squeeze all those gas particles down into a smaller container, there's now going to be more collisions. So if they're in a smaller container, those gas particles are going to be colliding with each other a lot more than they were when they're spread out into a bigger area. So that means if there's more collisions, the pressure is going to increase. So the pressure is all based on collisions. So anytime we increase the collisions of the gas particles, we're going to increase the pressure. And anytime we decrease the collisions of gas particles, we're going to decrease the pressure. And these are 3 ways, and we're going to, on the next slides, plug in some numbers with these so you can actually see how the math works. But these are 3 ways we can increase the pressure by increasing the collisions of the gas molecules. Like this first one here, you know, if you're pumping up a tire or a basketball or something like that, what you're actually doing is you're adding more gas particles into that container. So you can see as we add more gas particles, the pressure is increasing. And if you put too many in there, that the container can't hold any longer, it can explode and break. This middle picture is showing like what we were talking about by compressing a gas. Here we have gas particles in a 1 liter container, and then we decide to squeeze that down and compress them into a 1/2 liter container. Still the same amount of particles, but now they have less room to move around. So there's going to be more collisions, which is going to cause our pressure to increase. And then over here, the other way we can increase the collisions and increase the pressure is by heating it. So remember we said that the kinetic energy is related to the temperature. So if we increase their temperature, they're going to be moving around a lot more and have a lot more collisions. So as we heat it up, we still have the same amount of particles, but they're moving around a lot more and have a lot more collisions. So that increases the pressure. Okay, so now we're going to take those concepts and actually do some math with them. So what we're going to look at is 4 different gas laws today. This first one is called Boyle's Law. And it's named after, you don't need to know the name or dates. This is just to kind of, give you some background information. It's named after an Irish scientist named Robert Boyle back in the 1600s. And so what Boyle did is he looked at how pressure and volume are related. which is like that middle picture on the previous slide. So that middle picture looked at how, as we change the pressure and volume, what happens. And what he found is that the pressure varies inversely to the volume. So pressure varies inversely to the volume, which, as that middle picture showed, as we decrease the volume, we increase the pressure. That's what we mean by inverse relationship, is one thing goes down, the other thing goes up, and vice versa. So if we put that into an equation, what we come up with is P1 times V1 is equal to P2 times V2, where the P's are pressure, the V's are volume. So usually we say the 1's are the original pressure and volume, and the 2's are the new pressure and volume. Okay, so then as we plug in the numbers and solve for one of the variables, so as long as we have 3 of these variables, we can solve for the 4th. Like here, it says we have a gas of 242 milliliters in a container with a pressure of 87.6 kilopascals, the kPa, and we want to know what its volume will be at STP. Okay, so now it might be helpful if you go through and label, because this is like what you'll have on your homework, label what variables are what, but ultimately what we're solving for is V2. So we want to rearrange this equation to solve for V2 by dividing both sides by P2. So then we'll have P1, V1 over P2. And then we just have to go through and pick out which variable is which. So our P1 is the 87.6 kPa. Our V1 is 242 milliliters, and for these gas laws, we can leave volume in milliliters. We will next week take a look at a gas law where we will have to change that to liters. But in all of these gas laws, as long as our 1 units are the same as our 2 units, we can use any unit we want for volume. And then our P2, so if we're using kPAs here for our P1, what is standard pressure in kPAs for P2? Very good, yeah, 101.3. So we also want our pressure units to match. Now I suppose you could, if you didn't want to use kilopascals, if you wanted to put 1 atmosphere here, you could convert that, but that would be some extra work. So again, we need to make sure our units match. So the kPAs will cancel, and that's going to give us our volume in milliliters. Now before we calculate it, like we said, as pressure and volume are inversely related. So if we increase the pressure, what should the volume have done? We should decrease, yeah. So let's plug that in and find out. So we got 87.6 times 242, and then divide that by 101.3, and it did decrease. It went down to 209 milliliters. Okay, so that's our volume did decrease since we increased the pressure. And sig fig wise, the standard pressures, those got chopped off. Both of these numbers that we were given here had 3 sig figs. So again, as long as you're around the same number of whatever numbers you're given, you're fine. Now it did also give you temperature in STP when it told you STP, but did it say anything about the temperature changing? No, so even if it gives you extra information, if that extra information isn't doing anything, we don't need to include it. Okay? So everybody see how I got that? All right. So then our next gas law is called Charles's law, named after the French scientist Jacques Charles in the 1700s. And again, you don't need to know names or dates. Don't worry about that. And what Charles looked at is he compared volume with temperature. And what he found with volume and temperature is that they're directly related. So the volume of a gas varies directly to its Kelvin temperature. So that's the tricky thing about Charles's law problems is the temperatures, you can't plug in Celsius, even though you may be given Celsius for temperature in the question. You have to convert that to Kelvin. And who remembers how to do that? It's been a while. It's been quite a while. Okay, we have to add it, 273, and that is on your sheet. Okay, somewhere on here. Where did it go? Thought it was. Yes, it's right here in the middle. Okay, so anytime you plug in a temperature, and that's going to be true for all of our gas law problems that we're going to do, anytime you do math with temperatures, they've got to be in Kelvin. So you're going to add 273 to make it Kelvin. And so the equation we use for Charles's law is V1 T2 is equal to V2 T1. Okay, so notice in this one, the temperatures are on the opposite side. Where with Boyle's law, the ones were all together and the twos were together on the same side. Here, the T's are opposite. And that's going to be true in our other gas laws as well. So T's are always in Kelvin and they're always on the opposite side. So here we have a 225 milliliter container of a gas at 58 degrees Celsius. We want to know what volume it would occupy at STP. Now it's just a coincidence we're solving for volume, we're solving for V2 again. We can solve for any of these three variables in any of the gas laws. It just is a coincidence. So again, we need to get V2 by itself by dividing both sides by T1. So that will give us V1 T2 over T1. And so then we just plug in our variables. We've got our V1 of 225 milliliters. And then what would be T2? Right here. What's standard temperature? 0, which in Kelvin would be 273. Yeah, so we cannot use the 0. And why can't we plug in 0 here? What would that do to the problem? Yeah, if we multiply by 0 or divide by 0, we don't have any numbers anymore. Okay, so we always convert to Kelvin. So yeah, 0 degrees Celsius is 273 Kelvin. And then for T1, that's 58 degrees Celsius. So we need to convert that to Kelvin by adding 273, which is 331. And then our Kelvins will cancel, and that's going to give us milliliters. And again, before we solve the problem, we can get an idea of what's going to happen. Okay, so what we did is we decreased the temperature. So if we decrease the temperature, what should happen to the volume? Huh?
It goes up.
they're directly related. So if we decrease the volume, the temperature, the volume should also decrease. Yeah. So when we plug this in, let's see, 225 times 273, then divide by 331, and so yeah, our volume went down to 186 milliliters. So as with this one, as one goes down, the other one goes down. One goes up, the other one goes up. So that's what we mean by directly related. They're going to do the same thing. Everybody still with me? All right, and then I know this is a lot, so this is our final slide. We've got two more gas laws. The next one is Gay-Lussac's law, named after another French scientist, Joseph Gay-Lussac. Again, you don't need to know names or dates. This is around the 1800s or so. And what Gay-Lussac looked at is pressure and temperature. So he compared how pressure and temperature are related, and what he found is that the pressure is directly related to a gas's Kelvin temperature, or I should say directly proportional. So the pressure of a gas is directly proportional to its Kelvin temperature. Now that's a little different than Charles's law. Charles's law, we said they were directly related, meaning as one went up, the other went up. What's the difference with directly proportional? Your math teachers are cringing right now. So they're both going to do the same thing, but they're going to do it by the same increments. They're going to do it proportionally. So if we double one, not just will the other one go up, it's going to double as well. Or if we halve one, it's going to halve as well. So they're both going to do the same thing by the same proportion. Okay, so the equation we come up with for Gay-Lussac's law is P1T2 is equal to P2T1. Now I like to write it like this just because that's how we write the other gas laws, but oftentimes because this is a proportion, they're proportionally related, you'll often see them written as a proportion of P1 is to P2 as T1 is to T2, and then you cross multiply and divide. You're doing the same thing. It's the exact same math, it's just written differently. So whichever way you want to set it up, that's up to you. Okay. So the main thing is though temperature, we still have to plug in Kelvin. We cannot use Celsius temperatures in our math. It may give it to you in the problem, but you can't plug in Celsius in the math. Okay, so here's an example. Do not try this at home. This is not a smart idea. There's some gas left in an aerosol can at 1 atmosphere and 27 degrees Celsius. Somebody decides to throw it into a fire. We're going to solve for its pressure when its temperature goes up to 927 degrees Celsius. So for this one, we're solving for P2. So we're going to take P1 T2 over T1. So plugging in our original pressure, we have 1 atmosphere. And then our T2. Now again, even though this is a big temperature number, we still have to convert it to Celsius. So 927 degrees Celsius, when we convert it to Kelvin, becomes 1200 Kelvin. And then our T1, 27 degrees Celsius, is 300 Kelvin. And I chose these numbers just so you can see the proportion more easily. What did we do is we went from 300 to 1200 temperature-wise. We multiplied by 4, it quadrupled. So if they're directly proportional, what's the pressure going to do? Yeah, it's also going to quadruple, and that's exactly what it does. It becomes 4 atmospheres. And what do you suppose will happen to that aerosol can when the gas inside gets to 4 atmospheres? It's probably going to explode, yeah. That's why you never want to, whether it's an aerosol can or not, whether you think it has any gas inside, you never want to throw a closed container on a fire, because it will eventually explode, because there is gas inside. Unless you know for sure it's a vacuum, there is gas inside, and it will explode eventually. So yeah, not good. Sends shards of metal all over the place, hurts people. Yeah, don't do that. Okay, and then finally our last gas law is called the combined gas law. And this is what we use when, so far these other gas laws, we've only been changing 2 conditions and keeping 1 the same. The combined gas law is when we're changing all 3 conditions of pressure, volume, and temperature. And so the combined gas law looks like this. P1, V1, T2 is equal to P2, V2, T1. So again, just like we saw with the other gas laws, the T's are always on the opposite sides. We still have to use Kelvin for the temperatures. And this one is on your periodic tables. Okay, it's actually right across from, no it's not, it's a little above. Right, so it's right here on your periodic tables. And I only give you this one because as long as you know this one, you can do the other 3 gas laws. So like for Boyle's, all we have to do is take out the temperature. We've got Boyle's law. Charles's law, we just have to take out the pressure. And for Gay-Lussac's law, we just have to take out the volume. So you can use this for the other gas laws and just take out the variable that you're not changing. So you have this one, so you don't have to memorize any of them. Just know how to use it. So here we're solving. We have a gas at 75.6 kPa, 60 degrees Celsius, and 10 milliliters. We want to know what its new volume will be at STP. So in this case now we are changing both the temperature and the pressure, and we're trying to figure out what the new volume will be. So rearranging this to solve for V2, we're going to have P1, V1, T2 over P2, T1. Okay, so plugging in, and this is where you may want to label to help you keep straight which are 1s, which are 2s. So our original pressure is 75.6 kPa. Our original volume is 10 milliliters. And then our T2, our new temperature, is standard temperature, which again is 273 Kelvin. Cannot use Celsius. And then if we're using kilopascals here for our P1, that means we have to use the kilopascals for standard pressure for P2. So 101.3 kPa there. And then our T1, again we've got to change this to Kelvin, is 333 Kelvin. So our Kelvins cancel and our kPa's cancel, giving us milliliters. And then we just plug everything in. So the numerators all get multiplied. Here we have 2 denominators, so make sure you divide by both of them. So 75.6 times 10 times 273. And then we're dividing by 101.3 and divide again by 333, and that gives us 6.12 milliliters. Okay. So again, as long as you have this gas law, you can use that for any of them. Just take out the variable that doesn't change. Show your work. Okay, you gotta show how you set it up, and again, make sure your temperatures are in Kelvin.